We begin the third major concept of calculus, and that is the integration. And we're going to begin by developing definitions of the antiderivative and the indefinite integral. So just a quick summary of what we've done so far in calculus. First of all, we had to define this thing called a limit, which helped us define what was going on at a function as we approach a point from the left and the right. And the limit's necessary to get into the two major branches of this part of calculus. First, differentiation, finding the rate of change, the instantaneous rate of the change of a function at a given point. And differentiate, if you were to look it up, means to separate, to break apart. And that's exactly what we're doing when we're finding rates of change. So now we're going to go on to the third major concept in calculus, which is that of integration, and that's going to be our focus. Finding the original function if we know its rate of change. And integration is the opposite of differentiation. It means to build up things, to bring them together. So the antiderivative reverses the derivative process. It's the derivative in reverse. A function, let's call it capital F, is an antiderivative of some other function if we took the derivative of that function f and we got that other function. So let's try this. What is the antiderivative of 2x? In other words, what function gives me a derivative of 2x? What is the antiderivative of 2x? So if we took the derivative of this function we're going to find, we should be able to get 2x. Well, remember, integration is the reverse of differentiation. It is the antiderivative. So if our derivative has a degree of 1 and a coefficient of 2, and we go backwards from that to create the original function, well, we're going to build it up. So the new function is going to have a degree of 2 and a coefficient of 1. And you're going to say, ta-da! F of x has to be x squared, because if I took the derivative of x squared, I get 2x using the power rule. And you'd be right. But let's think about that for a second. What about x squared plus 1? If you took the derivative of that, you'd get 2x plus 0, or 2x. So both of these are the antiderivatives of 2x. In fact, the antiderivative of 2x is x squared plus any constant. And we're going to call that any constant c, where c stands for any constant we want. So really, interestingly enough, there are an infinite number of functions that are the antiderivative of 2x. X squared plus any constant will give you that. So let's look at this graphically. And I've graphed f of x equals x squared plus c, just 4 of the infinite number of possibilities, all just vertical shifts from the original parent function of f of x equals x squared. All of these functions have a derivative f prime of x equals 2x. No matter what constant you put in, you're always going to get 2x as a derivative. And let's kind of visually look at that. I'm highlighting the tangent line. You can see them in black at these points A, B, C, and D that are at x equals 1 along all 4 of these parabolas. And you can see the slope of that tangent line is the same at all 4 points. And indeed, if I move this anywhere else on the parabolas, you'd see the same thing. For instance, at x equals -1, I've got these points A, B, C, and D. You can see the slopes of these tangent lines are the same. No matter where I move them, they're going to be the same. So what that means is there's a whole family of functions, x squared plus c, that are the antiderivative of 2x. All of these functions have a derivative of 2x. So let's put some symbols to this. The family of all the functions that are antiderivatives of the function, we call that an indefinite integral. And the integral symbol is this giant elongated S. And the S stands for summation, which you're going to find out more about later, but the integral builds things up. It sums things together. We're going to use this special symbol to denote integration. The function we are trying to integrate is called the integrand. The variable we are integrating with this is that dx part that's inside this integral, is called the variable of integration. And never leave that off, because that tells us what variable we're integrating with respect to. And so the family of all those functions is the integral, the indefinite integral of f of x dx. So for the example we just did, we would say the integral of 2x dx is equal to x squared plus c. In other words, x squared plus c is the family of functions that are antiderivatives of 2x dx. 2x is the integrand, the thing we're integrating. Dx is the variable of integration, the variable we're integrating with respect to. And the family of functions we get when we integrate that are x squared plus a constant of integration. An integration process, it doesn't result in just one answer, because there are, as we saw earlier, an infinite number of possibilities of functions that have a derivative of 2x. That's where that constant of integration comes in. So in class, we've developed some rules for integration. And since integration is the antiderivative, basically we're taking the derivative and going backwards. If they're very much tied, integration rules are very much tied to the differentiation rules, just in reverse. So for example, let's look at the derivative of a constant. Well, the derivative of a constant is 0. Therefore, the antiderivative, or indefinite integral of 0 dx, is equal to c. So the derivative of a constant is 0. The integral of 0 is a constant. The derivative of a constant times x is equal to the constant. For example, the derivative of 3x is just 3. Well, then it follows then that the antiderivative of a constant dx is equal to the constant times x plus c. Constant multiple rule. The derivative of a constant times f of x is just equal to that constant times f prime of x. Therefore, the integral, or antiderivative, of k f of x dx is equal to k times the antiderivative of f of x dx. In other words, we can take that little k, if it's a constant, only if it's a constant, and move it outside the integrand. The sum and difference rule for derivatives is the derivative of f of x plus or minus g of x is equal to the derivative of f of x plus or minus the derivative of g of x. We can reverse that in integrals as well. The integral, or antiderivative, of f of x plus or minus g of x is equal to the integral of f of x dx plus or minus the integral of g of x dx. In other words, just like we can separate the derivatives, we can separate the integrals. Next, we have the power rule. The power rule for differentiation, if we have a function x to the n power, it's n times x to the n minus 1 power. If we do that in reverse, it's a little bit more complicated, but the integral of x to the n dx is equal to x to the n plus 1 divided by n plus 1 plus c. As long as n does not equal to negative 1. We're going to deal with that a little bit later when we get into transcendental functions. So again, integration typically raises the function's degree by 1 because taking the derivative lowers it by 1. So we're going to raise the power by 1, and to account for the coefficient, we're going to divide by n plus 1. Trigonometric functions, of which I've only put one here, work the exact same way too. If you know the derivative and you go backwards, you find the integral. Since the derivative of sine of x is equal to cosine of x, it follows that the integral, or antiderivative, of cosine x dx is equal to the sine of x plus c. All of the other trigonometric functions work the same way. Let's look at some examples of the rules that we just talked about. So if we wanted to find the antiderivative of 3dx, or the integral of 3dx, it is going to be 3x plus a constant c, because the integral of a constant is the constant times x plus c. Now, by the way, you can check all the integration that you do by taking the derivative, because the derivative and the integral are opposites of each other. So if I took the derivative of 3x plus c, I get 3, which is my original integrand. So that's a great way to check your work when you're taking integrals. So let's look at the integral of 5x squared dx. What function has a derivative of 5x squared? So that's equal to 5 times the integral of x squared dx. Notice we use the constant multiple rule to move that 5 outside the integrand. And that is equal to 5 times x to the third power over 3, x to the n plus 1 over n plus 1. In this case, n is equal to 2, using the power rule of integration. Common mistake in integration is to forget that plus c. Because remember, there's an infinite number of functions that have that derivative of 5x squared. And in a simplified form, it's 5/3 x to the third power plus c. If we took the derivative of this, we would get 5/3 times 3 times x squared, which would be 5x squared. So let's look at the integral of 4x minus 6 dx. So we can use the sum and difference rules to separate this into two different integrands. So it's equal to the integral of 4x dx minus the integral of 6 dx. Well, let's solve each one of those. The integral of 4x dx is equal to 4 times x to the second power over 2, using the power rule, and the constant multiple rule, plus c1. Let's call the constant of integration from this integral c1, minus the integral of 6 dx, which, as we know from the constant rule of integration, is just 6x plus c. So we put the minus in front of that entire term, and that's what we get. So this looks a little bit more complicated, but as it turns out, C1 and C2 can be combined into just a constant of integration c. So our final answer after simplification is 2x squared minus 6x plus c. And you're probably legitimately wondering what happened to all those constants. In the end, actually, it doesn't matter. We're going to show you in more detail when we get into definite integration, but in the end, it doesn't matter. And oh, by the way, if you check this by taking the derivative of 2x squared minus 6x plus c is indeed 4x minus 6, our original integrand. So this checks out. We'll do a final example from trigonometry, the integral of 5 sine x dx. Well, we're going to use the constant multiple rule first, separate the 5 out of the integrand, so it becomes 5 times the integral of sine x dx. And we know that the integral of sine x dx is negative cosine x plus c, so the answer becomes 5 times negative cosine x plus c. And when we simplify that just a little bit, the final answer is negative 5 times the cosine of x plus c. We can always check our work by taking the derivative. The derivative of negative 5 cosine x plus c is negative 5 times the negative sine of x, which is 5 times the sine of x, our original integrand. So it checks out. So that's a summary of the beginnings of integration. Integration as the antiderivative, taking the derivative in reverse, turning it into its original or parent function, which leads to an infinite number of functions, only different by a constant.